Imagine this. You're sitting on a staggering 401 billion tons of coal, but at the exact same time, you are bleeding billions of dollars every single year just to import the foundational chemicals your country needs to survive. It's a massive energy paradox, but that is the reality of India's current industrial ecosystem. We aren't going to talk about burning more coal for power today. Instead, we're looking at a process called coal gasification. It is an urgent, highly complex, and strategic modern alchemy that India absolutely needs to transform its resource base into true industrial sovereignty.
So how exactly do you turn dirty coal into clean fertilizer? It kind of sounds like a trick question, right? How do you take a solid, dirty lump of coal and turn it into life-sustaining fertilizer for agriculture or pure methanol for industry? Well, that's exactly what we're going to explore in this explainer. We're not talking about just tossing coal into a furnace and watching it go up in smoke. We're talking about fundamentally altering its molecular structure, literally breaking it down chemically and rebuilding it into something incredibly valuable.
Okay, let's walk through our roadmap. 1. The need for gasification. 2. Coal basics and the process. 3. Syngas to strategic products. 4. India's high ash challenge. And finally, 5. A strategic path forward. Let's dive right in.
Part 1. The need for gasification, resource sovereignty.
To really grasp why this technology is an absolute must-have, we first have to understand India's immense vulnerability. You see, despite having vast domestic energy resources, a huge chunk of India's chemical and fertilizer supply chains relies heavily on imported hydrocarbons. Just look at the import dependence for a vital chemical like methanol. India consumes about 4.3 million tons of it annually, but over 90% of that is imported. And methanol is everywhere. It's in plastics, solvents, and emerging fuel blending programs. So relying on imports for over 90% of such a critical industrial building block, that is a profound strategic risk.
And that risk comes with a staggering price tag. By substituting these chemical and fertilizer imports through domestic coal gasification, India could save an estimated $30 billion per year. Take a second to let that number sink in. $30 billion. That's money retained within the domestic economy, shielding the country from global supply shocks and drastically reducing the foreign exchange burden. But to actually unlock those savings, we need to understand the underlying science.
Which brings us to Part 2. Coal basics and the process, unlocking the chemistry.
Now, to master this industry, we have to master the raw materials. And trust me, not all coal is created equal. First, we need to talk about ash. In simple terms, ash is the unburnable rock and mineral residue left over when coal is consumed. When we discuss coal gasification in India, ash is essentially the central villain of the story. High ash content means you're processing a whole lot of useless dead weight. It wreaks havoc on equipment, causes severe wear and tear, and just drastically drives up the cost of the entire operation.
Next up, let's look at lignite. Lignite is a low-rank, brownish coal. India has roughly 47 billion tons of it, mostly sitting in places like Tamil Nadu, Gujarat, and Rajasthan. Lignite is super fascinating because its carbon structure is highly reactive. We're talking up to 10 times more reactive than harder coals. That makes it mathematically excellent for gasification. But there's a catch. It has a massive drawback. It is extremely moisture-rich, sometimes up to 66% water. Because it's so wet and prone to spontaneous combustion, you really can't transport it very far. You basically have to process it right at the mine mouth.
And all of this leads us to syngas, or synthesis gas. This is the magical intermediate product we've been hunting for. Syngas is essentially a purified mixture of carbon monoxide and hydrogen. Think of it as the ultimate blank chemical canvas. Once you have syngas, you've unlocked the door. You can tweak the ratio of hydrogen to carbon monoxide to produce almost whatever industrial chemical your economy requires.
This brilliantly illustrates the difference between what we usually do with coal and what gasification actually does. Combustion is just burning coal completely with oxygen. It destroys the chemical structure just to release pure heat. It's exactly like burning down a forest just to stay warm. Gasification, on the other hand, restricts the oxygen and adds steam. It stops short of complete burning, purposefully retaining the chemical energy inside that syngas. It's the equivalent of carefully harvesting the wood from the forest to build a house, piece by piece.
So how does this magic actually happen? Well, it happens in 6 highly controlled steps inside these massive pressurized vessels called gasifiers. Step 1 is drying, where temperatures hit around 200 degrees Celsius to bake out the moisture. Step 2 is pyrolysis, where volatile gases separate from the solid carbon, leaving behind a carbon-rich char. Step 3 is partial oxidation, where limited oxygen is introduced to create the intense heat needed for the next step. Fourth is the crucial reduction phase, where that char reacts with steam to finally form our syngas. Fifth is gas cleaning, which meticulously strips out the bad stuff, things like carbon dioxide, ash particulates, and sulfur, which is a highly corrosive impurity that damages both equipment and the environment if left unchecked. And finally, step 6, product conversion, where that purified syngas is chemically tuned to become our final strategic output.
Moving on to part 3, syngas to strategic products, the chemical landscape.
Now that we've successfully created and purified our syngas, what do we actually do with it? The array of outputs is honestly staggering. You can synthesize ammonia and urea, which are the absolute bedrock of India's agricultural fertilizer and food security. You can produce methanol for chemicals and fuel blending. You can create synthetic natural gas to pump directly into city gas grids. You can even use syngas for direct reduced iron to manufacture steel without relying on expensive coking coal. And crucially, you get valuable co-products out of the deal: sulfur, captured CO2, and phenols. In fact, globally speaking, the ability to sell these diverse co-products is the single strongest predictor of whether a plant will actually survive commercially. Breaking down these target markets reveals India's master plan. The government isn't just throwing darts at a board. Their approach is highly targeted. Ammonia and urea face a massive 17 to 19 million ton annual domestic demand. Methanol, as we saw earlier, is almost entirely imported. Therefore, these two are the absolute primary focus of India's policy. Things like blue hydrogen are secondary because they require complex carbon capture and storage to work. And generating power via gasification, that's the absolute lowest priority because it has a historically weak commercial track record worldwide. The policy zeroes in exactly where the import substitution impact is the highest.
Part 4, India's high-ash challenge, the geographical dragon.
Sure, the science works beautifully on paper, but India's actual geology complicates this dream immensely. We have to confront the geographical dragon in the room, India's high-ash coal. Take a look at the differences here. 87% of India's coal reserves used for power are bituminous or subbituminous, and their ash content is astronomically high. We are talking between 35 and 50%. Their chemical reactivity is also relatively low. Lignite, on the flip side, has low ash and high reactivity, making it a great feedstock. But as we discussed, its extreme moisture content and tendency to spontaneously combust means you are locked into building your plants right next to the mines. The harsh reality is that the vast majority of the coal India wants to monetize is highly quality disadvantaged.
To really put this into perspective, Indian bituminous coal averages around 45% ash. Compare that to imported coal, which usually sits way down below 10%. Standard, globally available gasifiers were designed for that 9% imported coal. So when you try to feed them Indian coal, they literally choke on the unburnable rock. It causes slagging, refractory wear, and terrible carbon conversion rates. This is exactly what caused severe operational strain at early Indian plants when ash levels started creeping past 30%.
And the direct economic consequence of this geology is brutal. Because the coal is nearly half ash, you have to build much larger gasifiers just to get the same amount of useful syngas. You need more oxygen, more auxiliary energy, and massive ash handling systems. Independent analysis estimates that specifically in India, the capital cost of the gasifier alone accounts for a staggering 30% of the total syngas production expense. This is why indigenous technology, like custom fluidized bed gasifiers designed specifically for high-ash coal, are so vital to making this whole thing economically feasible.
Finally, Part 5, a strategic path forward, policy and reality.
We know the prize is huge, and we know the hurdles are monumental. So how is India actually navigating this? Well, the government announced a massive 37,500 crore rupee outlay for the surface coal gasification scheme. But what makes this policy genuinely smart isn't just the size of the check, it's how the money is distributed. It uses milestone-linked disbursements, divided into 4 equal 25% installments. Developers only get paid when they secure land, when they infuse equity, when they commission the plant, and crucially, only when they sustain actual commercial production for a full year. This brilliantly protects public money from just being sunk into abandoned, half-built mega projects.
Looking at the timeline, you can see a rapidly accelerating ambition. The National Mission launched back in 2021. The flagship Tulcher Fertilizers project, a massive coal-to-urea plant blending domestic coal with imported petcoke, is slated for commissioning around 2027. The headline goal is gasifying 100 million tons of coal by 2030 and a whopping 250 million tons by 2047. However, I definitely have to caution you here, given the long construction periods and the massive technical hurdles of high-ash coal, these targets should really be viewed as a directional policy ambition and intended scale rather than a guaranteed delivery date.
To actually hit those ambitious targets, experts agree on a few non-negotiable recommendations, because just throwing money at the problem isn't enough. First, continue basing all public support on verified performance. We can't subsidize inefficiency. Second, strictly match technologies to local geology, using those fluidized beds for high-ash coal. Third, these plants require immense amounts of water, so protecting basin-level water resources is absolutely critical. Fourth, we need true indigenization of the complex chemical catalysts. And finally, we have to address the environmental reality by mandating strict carbon capture and storage.
Because here is a really sobering reality check. Strategic success does not automatically equal climate sustainability. Gasification might reduce local particulate pollution compared to just burning coal? Sure, but unabated coal-derived methanol and ammonia are substantially more carbon-intensive than producing them from natural gas or green hydrogen. Without functioning large-scale carbon capture and storage infrastructure, which, by the way, is still entirely unproven at scale in India, this technology carries a very heavy global carbon footprint.
Which leaves us pondering one massive final question. India's quest for resource sovereignty is undeniable, and saving $30 billion a year through gasification could completely transform its industrial landscape. But can India master the alchemy of its uniquely challenging high-ash coal while simultaneously meeting the unforgiving demands of a carbon-constrained future? The answer to that question will literally define the next 50 years of the country's energy security. Thank you so much for joining me for this explainer. I hope it helped you see the incredible complexity and potential behind this modern alchemy.